All right, so I'll go ahead and get started. Those of you that may have been in attendance last summer at the first annual meeting, I gave a talk where I kind of defined this term scientific machine learning. And what I talked about last summer was very much an overview talk. And today, what I'm going to do is dive into a few examples that we've worked on, generated some results over the last year. This talk is also a kind of an abbreviated version of a longer talk that I've given twice in the last few months. So if you find anything I say here interesting and you want more detail or specifically more background, I've kind of cut out some of the background material here. Then you can reach out to me because those talks are actually recorded. They're on YouTube. I can point you to them if you'd like. So I'll start off with, again, just a quick introduction to what I'm talking about when I say scientific machine learning. There's some other kind of terminology that's been evolving. My favorite is scientific machine learning. There's even a website, SciML.ai. There's some other ones, theory guided machine learning or theory guided neural networks, physics informed neural networks. I'm going to say that those are kind of subsets of the overall theme here. When I say scientific machine learning, what I'm talking about is, processes that workflows, things we do in engineering sciences that sit at the intersection of traditional computational engineering, which involves the solutions of ODEs and PDEs, and the biggest example of that, of course, in our world of petroleum engineering is in reservoir simulators. There's many others, but that's one example. And then statistical estimation, machine learning, AI, whatever you want to call it, which I've illustrated there as a small neural network. So things that sit at the intersection of these two disciplines are what I'm talking about when I'm talking about scientific machine learning. A few like concrete mathematical examples. The first one is something we've done for a long time, quite a long time in engineering, and that is to use the solution of ODEs, PDEs to just generate synthetic data. So we would basically, and even some of the talks this morning, we're doing this very thing, right? So you're using a reservoir simulator to generate synthetic data, and then using that as data to build surrogate models or estimators. So in these examples, when I have a hat above you, it's a parameter that I'm estimating. In this case, parameterized by theta, some parameters. So we've done this for a long time, using physics solutions of ODEs, PDEs to generate data that we'll use for surrogate modeling. So I'm going to include that in scientific machine learning. Something that's been around for a handful of years now, so-called PINNs, physics informed neural networks. I think that term was actually coined in a 2018 paper by guys at Brown, George Karniadakis, and that seems to be the term that's sticking, physics informed neural networks. Again, there's a similar terminology called theory guided neural networks. So you see that in some papers and other things, but the idea has been around much longer. I saw a paper from 2006 recently where they didn't call it physics informed neural networks, but they were doing this very thing. And that is, you basically, and normally in machine learning model, we have some data, and we have some estimation, some estimator, hat, parameterized by theta, and our goal is to find the theta that minimize some normed quantity between the data and the estimated or the prediction. In a physics informed neural network, we add to this objective function, the standard kind of L2 objective function, we would add this idea of minimizing the solution to the balance laws themselves, right? So here we have a balance law represented by u prime being a time derivative minus some function of u. I say time derivative, it could be spatial derivative too, but basically some balance law that we're also going to include in the objective function, so that not only are we're trying to find the parameters of theta of the estimator that minimize this whole thing, so that the the objective function is regularized by the balance law, right? And when I say balance law, conservation of energy, mass, momentum, right? Things we do in engineering. More recently, this idea of neural differential equations and also universal differential equations, which I guess neural differential equations are a subset of. So in this setting, we have, basically we're going to try to solve this type of equation where on the right-hand side, we could have some, say, differential operators on our quantity of interest U, but also some unknown physics, if you will, that we could represent with the neural network parameterized by theta. And the goal would again be to basically solve this equation at the same time we're finding an optimal set of parameters that give us the correct solution to the equation. So these are examples, just kind of high-level examples, and I'll break right into a few of kind of real examples that we worked on over the past year in my group that have some application to petroleum engineering. And these are quite academic examples, but you have to crawl before you can walk. So this example could have implications in, say, seismic inversion and other things, where the idea here is that we're trying to understand the elastodynamics of heterogeneous materials, right? So say we have in this case, just a one-dimensional bar, and each, cell of the bar could be made up of, like, in this case, we're using a periodic microstructure. So in this case, just alternating materials that have differing Young's modulus and densities. And we're going to apply a load to the end of the bar, and we want to see is like the dynamics of how this changes, of how the wave mechanics changes as it runs along the bar. Now, because we're interested again in like petroleum reservoir size domains, we're not ever going to go in and discretely model every grain in an entire kilometers wide reservoir, right? So what we're interested in is well, I guess I'll just say that, if we were going to model every grain, right, then we could just use the classical equations of elasticity, right? Cauchy's equation. This is just Newton's, this is PDE, that's Newton's second law for continua, right? Conservation of linear momentum, along with Hooke's law. And if we wanted to, we could discretize, every individual unique material in the domain, and we can solve this equation. But again, this is not realistic in like a petroleum reservoir setting. So what we're more interested in doing here is considering something like this, where we're not going to consider the microstructure. However, the microstructure greatly influences the wave dynamics, right? Those materials, because they have differing Young's moduli, they have different mechanical impedances, and you get wave reflections, which on large scales cause wave dispersion, right? So the waves spread out over time. And we're interested in trying to capture, or trying to have a model that can capture those kind of effects, so like large scale dispersion of waves over long distances. And one way to do that is to use something that, and the physics here, not that, well, it's the equation we're solving is not that important. It's not kind of the point of what we're doing, but we chose to use something called a paradynamic momentum equation. This is a about 20 years old theory that generalizes classical Cauchy equations, so that now instead of having that divergence of stress term to represent the internal force in the material, we have this integral functional that you can visualize or think of mathematically as like a kernel convolved with this difference in displacements. And we've shown it's, fairly rigorous mathematical theory behind this. It shows that in the limit of this domain of integration shrinks to a point, then you recover classical Cauchy theory as a result. So this is like a generalization of classical continuum mechanics. And the benefit of this is that, because it's an integral differential equation, now we can actually model wave dispersion. So the local PDEs are non-dispersive. And so here we can actually model wave dispersion with this. So the idea of what we're going to try to do with this equation, we're going to try to basically learn the kernel function that matches that in dynamics of the wave mechanics. So essentially learned the kind of large scale material behavior that is occurring because of these wave reflections due to small scale heterogeneities that we don't want to model, right? Because it's just not physically possible, or really it is physically possible, but there's just not computers big enough in the world to solve those kinds of problems on reservoir scales, right? So if we kind of do this, and I'm jumping ahead quite a bit here, but basically the idea is that we discretize that bar first with the finite element method, solving the classical Cauchy momentum equation, including all of the different species, so that we capture all the wave dynamics and everything accordingly, and then we use that to train to train a machine that can learn the kernel function, right, in that paradynamic momentum equation. And so what I'm plotting here is the midpoint displacement. The orange line is the FEM, fully resolved simulation data. So again, including the differing species. And the blue line is this so-called paradynamic solution where we've learned the kernel. Now we only use a very small amount of training data. So we're using the FEM data, the finite element method data, as the truth solution, right? And we're only using a very small amount of training data. So just very early in time, and then we're using that to predict the rest of time, right? So here is the midpoint displacement at a time much later. The wave has already passed through this small amount of training data. And I'll explain what I mean by this without constraint here in just a second. But basically, this is how how our prediction does. And you can see again, you have this dispersive behavior of the waves due to the heterogeneity, right? And so, if we would have trained a large scale coarse model without including the heterogeneity and say solved it with the finite element method, the orange line wouldn't have any of these oscillations, right? Because again, there's no dispersion in the classical method, right? So the paradynamic method, does pretty well. We say without constraint. I'll explain that in the what's to come here. So here we add a physical constraint. So we know that like classical homogenization theory would give us a homogenized elastic modulus of something like this. Well, and we can basically compute this kind of averaged moduli over all of those unit cells and include that as a constraint in our objective function. So I'm not showing all the details, but if we include that as a constraint in the objective function, then all of a sudden, what was pretty good prediction before becomes a much better prediction now. So you can see our model, again, I'll say this one last time, the FEM model includes all of the heterogeneity. It actually discretizes every change in the material properties of the unit cell, whereas the blue line, the paradynamic model, basically we just learned that kernel function, which includes the effective properties of that. And by adding this physical constraint, we can see we improve the prediction. And this is even more apparent. Well, first of all, if we just look at the testing error, right? So this is the testing error. And in our case, the testing data is always in the future time. So we're predicting into the future. We train for a small amount of time, and then we predict into the future and compare the two. And so you can see that this inclusion of the constraint. So if we use the constraint, this what we call energy constraint effectively, then what that turns out is that with, we can ultimately get the same amount of accuracy either way, but it requires a lot more training data to do it without the constraint. So just knowing a little bit about the physics, adding that as a constraint of the objective function allows us for a more accurate prediction with much less training data. And this is even more apparent in 2 dimensions. So in 2 dimensions, again, we kind of have an idealized scenario here, but now our unit cell looks like this. So again, differing Young's moduli and density, and we're using this type of arrangement. So you can think of this as like a compliant particle embedded in a stiff region. The orientation or the actual values here, we've shown that, you know, it works. It doesn't matter if, say, you flipped it. If you had a stiff grain embedded inside of a compliant region, it would also work. But again, the difference is quite apparent here, right? So in the first example on the left, you know, we don't have a constraint, and you can see, so we use this amount of training data, and you see in the region of training, they match perfectly. But then when we begin our prediction into the future, the results diverge quite a bit. And by adding this energy constraint, then again, now we have a much better prediction into the future, right? So that's one example, you know, again, for you know, looking at wave dynamics. And who could do machine learning in the field of petroleum engineering without looking at the Buckley-Leverett problem? So if you've done anything with respect to reservoir simulation or reservoir engineering, you've probably studied the Buckley-Leverett problem exhaustively. I know as an undergrad here at UT in our courses in reservoir engineering, there's actually 3 course sequence, reservoir 1, 2, and 3. And in all 3 of those courses, the Buckley-Leverett problem is covered. So the Buckley-Leverett problem, of course, has to do with, it's kind of the classical validation problem for any kind of 2-phase, you know, black oil reservoir simulator. And that's because you can reduce it down to, under certain assumptions, you can reduce it down to something that's 1D, essentially one equation that can be solved with the method of characteristics semi-analytically. So you have like a semi-analytic solution to compare to. Again, yeah, this is just that's just what it can be reduced to under these assumptions, where you have this kind of relative permeability, Darcy's law, and this is how we define the so-called flat fractional flow curve, and everything can be reduced under certain assumptions to this one equation, which you can solve semi-analytically. So Tshelepi's group at Stanford looked at this problem about a year ago, when physics-informed neural networks were gaining some steam. And they tried to solve this problem with the standard kind of physics-informed neural network. So again, I kind of described this earlier, but you know, here we have our standard kind of neural network would be on the left, standard representation. But on the right, we have now differential, you know, we basically differentiate the solution of the neural network and combine those to compute some loss function. In this case, the loss function is the balance law, right? So this term right here is included in the loss function, whereas the saturation is determined by a neural network, right? So been a lot of talks already on neural networks, so I won't go into the details of the construction. But basically, when you know, looking at Tshelepi's work, they showed that, you know, for these kind of concave flux functions, which is that fractional flow curve, then, you know, the solution would do well, right? And again, you have an exact solution there, so you can compare to. However, no real world problem really has that kind of concave flux functions. They're always non-convex like this. And then all of a sudden you start to see problems with the neural network solutions, and they weren't performing well. They also looked at convex, which in the case of a convex flux function, you just get this step change and you get a discontinuity that propagates through the solution. And again, the neural network, or physics-informed neural network, did not perform well. So the way they chose to solve this was by adding this artificial diffusion term to the balance law, right? So, and included that in the objective function. And what they showed is that, you know, as this epsilon approaches 0, well, then this approaches the standard, you know, Buckley-Leverett balance law. But with this little bit of artificial diffusion, they could get some nice predictions, right? And you know, they showed it also for the convex case. And here's the different, basically the loss functions over, you know, epochs of training in the solution of the neural network. They showed that, you know, again, for large values of epsilon, you could get very fast convergence. But for small values of epsilon, including epsilon equals 0, you get, divergence or very stagnated convergence. And so this is the way that they chose to solve the problem. So the way we took a different approach, we used something called a hp-VPINN. So HP kind of comes from the finite element world, given that you can have, say, h-refinement and p-refinement, which I have an example of what that is. And then the VPINN just stands for variational physics informed neural networks. So here in the balance law, instead of using the continuum balance law, we're going to use the weak form of the balance law as we would in, say, a finite element solution. So in this, in construction of the loss function, we have the balance law itself. This L is just a differential operator on the neural network. And then these are just boundary conditions. So essential boundary conditions, Neumann boundary conditions, and initial conditions. This is one thing I'll point out whenever you see some fantastic results and everybody gets excited about these physics-informed neural networks. Recall that the boundary conditions themselves are embedded in the objective function, which means if you change the boundary conditions, you have to retrain the network to get a solution. And by the way, training the network is much slower than just solving these problems with standard technique. You can just solve it with the finite element method much faster than you can train the neural network accurately. So, in our hp-VPINN formulation, now we're using this instead of the continuum form of the balance law. We're using the weak form of the balance law, and we have various test functions Vj that we're multiplying by. And so our total loss function looks like this. Again, the residual from the weak form, the essential, the Neumann boundary conditions, and the initial conditions. And this is what we kind of mean by H or P refinement. So in that test function, that Vj in the previous equation, those represent polynomials. And what we can do is we can either basically have more subdomains that we compute the integral over, or we can have more polynomials that we include. And so more subdomains would be H refinement, more polynomials would be P refinement. And so here's an example which just demonstrates that. Here we start with 2 subdomains with 5 polynomial test functions. If we just do P refinement, then here we're going from 2 subdomains with 5 test functions to 2 subdomains with 10 test functions. And then over here is an example of H refinement. So again, 5 polynomials, but this time with 5 subdomains instead of just 2. So that's what we mean by H and P refinement. And we show that, in doing this, again, with the Buckley-Leverett problem for our residual, then we can get nice solutions, fairly accurate solutions. And there's no, right now, this is kind of just a demonstration. There's no theory about exactly how to do the HP refinement. So like in the world of finite elements, we have spectral methods, we have, things like discontinuous Petroleum methods that can give us like an actual theory to tell us exactly how to, do the refinement so that we can get convergence in any norm we want. But, right now it's too early to really know how to do this. We're kind of doing it naively, but nevertheless, it does work. We don't see those problems with convergence like Tshelepi showed with the continuum version of the loss function. So having said all that, you might have noticed in there on the previous slide when I kind of poo-pooed the fact that even though we can do this, maybe you shouldn't, because you can solve this much faster with just using a standard finite element solution. So, so just because we can doesn't mean we should. However, there is one case where it might be useful to do that, and that is if you're interested in solving the inverse problem. So in this case, now we're interested in, given the data, we want to find the constitutive model. And the constitutive model in this Buckley-Leverett problem is this fractional flow curve, right? And so we're gonna do this in 2 ways. We're gonna randomly sample the data. So this is the XT space, and these are values of saturation in that space. And we're just gonna sample the data randomly and train our model with that data. And in the other case, what we're going to do is we're going to only sample at the end, right? So this would be more analogous to something you could actually do in the laboratory. In fact, it's what we do. So you're doing a core flood, you're flowing water through a sample, and on on the outlet side of the sample, you measure the saturation. And so that's what we're doing here, right? So for all time at x equal to 1, which is the end of the sample, we're going to measure the saturation. And we're going to see if we can then find, or, solve the inverse problem. And this is where there is some utility in these so-called physics-informed neural networks, because you can actually solve the inverse problem at the same time you solve the solution, right? You find the solution. So in this case, we have two neural networks. We have a neural network on the solution, and we have a neural network for the fractional flow curve. We do add a couple of constraints that these are things that we know. Basically, the fractional flow curve must be 0 at 0, and it must be 1 at 1. A function of evaluated at 1, it must be 1, and otherwise it must be 0 evaluated at 0. And then we constrain it at the points that we know the data, right? So we just add these two additional terms to our loss function from before and train the model. And in this case, now we actually learn the fractional flow curve at the same time we learn the solution, right? And so in this case, you can see it works well. And this is the randomly sampled, and this is the sampling only on the outlet boundary, and both methods work just fine. And so we actually learn the constitutive model, the unknown material properties, in the training of this. So this is documented in this paper, and I think this says submitted, but the paper's actually been accepted now. So when we're talking about this kind of SciML, there's some pretty key computational considerations that come up, and that is, if we have something like this, where we have basically a neural network that represents some part of the constitutive model. So this would be the pressure diffusivity equation, where the mobility is unknown. And so we're going to plug in a neural network, and we're trying to basically learn the physics of the problem. We're trying to learn the constitutive model. And in trying to solve a problem like this, what we want to do is we want to find the parameters of the neural network theta that minimize this objective function. Basically we're trying to, this is solving the pressure diffusivity equation here, and we're trying to compare that with some known data and try to find the neural network that we can come up with that minimizes this objective function. And the trick here is that we have to basically compute derivatives with respect to theta through the integration of a differential equation. And this is not trivial. There aren't software packages out there that are just readily do this. You can't just stick a neural network in for your constitutive model and hand it over to Abacus or ANSYS, standard finite element tools, and have it train the neural network and give back your answer, right? So one approach that we've started to take is we're actually starting to develop finite element solution tools within the neural network frameworks themselves. So the neural network frameworks, we think of them as neural network tools, but they're also just accelerated array computation tools. In the Python world, we're most familiar with TensorFlow and PyTorch. My favorite is actually JAX, and I'll talk a little bit more about that in a second. And then in the Julia world, there's a good one called Flux. But the idea here is that instead of, what we'll do in this little quick example I have next, we're actually going to implement the finite element solution technology within JAX, and then it allows us to just embed a neural network right into the solution, right into our finite element solution, and we can train it, and everything works fine. And the great thing about JAX, of course, if you're familiar with Python and you know NumPy, well, JAX implements the NumPy API, basically all of it one-to-one, and most of SciPy. And what you get on top of that is you get GPU, TPU acceleration. So you can run these on NumPy arrays on GPUs. You also get just-in-time compilation, including compilation to the GPU, if that's what you're interested in. And you get framework-wide automatic differentiation. And if I have framework-wide automatic differentiation, then I can train a neural network, right? So, if you've ever coded up your own like Newton solver for a nonlinear problem, I just put the actual code here. So this is one step of a Newton iteration, where this residual is a function that computes the finite element residual And if I want to compute the Jacobian with respect to that in JAX, all I have to do is just call this one function right there. It automatically constructs the Jacobian for me that could include with respect to, if the residual has a neural network in it or anything like that. Then I can just hand it off to a linear solver, which is also implemented in JAX, that just needs this Jacobian vector product to compute an update direction, and then I can add that, right? So this is one step in a Newton iteration. And if you're interested in looking at all the code of this example I'm about to show the results to, it's on my blog, the whole code. You can just download it and run the whole code, training a neural network inside the solution of a finite element discretization. So over here on the left is our forward problem. So this is the solution. Again, the steady state pressure diffusivity equation, given a known mobility function. So in this case, the mobility function is x cubed plus 0.001. This is what I use to generate this solution over here, right? So this is my mobility function curve. That's a function of space. And the black line is the solution. And so then if I basically, instead of, this, I use this as the data that I then use to train a neural network. So in the second example, I replaced the known mobility function with an unknown, just a neural network. And in this case, a very, very small neural network. It just has 4 nodes in the hidden layer and a tanh activation function. That's it, one single hidden layer with 4 nodes and a tanh activation function. And I trained that neural network through the solution of the differential equation, again, in my JAX code. And I actually learned the mobility function, right? So that line there, the red line represents the learned function and the black line represents the known function in which I generated the data. The beauty of this method is that I can then go on and solve problems with different boundary conditions. So once my neural network is trained, I can change the boundary conditions and I can go on and solve the forward problem in a standard way with my finite element model, and I get the correct answer in a short amount of time. Right? So, in summary, SciML models can learn with small data, as I kind of demonstrated, because you have the physics or part of the physics in the objective function. Nothing regularizes these things better than the physics or the bound laws themselves. And so, we can get by with smaller data. I had a couple examples where I showed that, and then, it also extrapolates. In all my examples, I'm extrapolating in time, predicting into the future. And in the, particularly in the last case, they're far more interpretable because, in the last example, all I'm doing is learning the unknown constitutive model. The balance laws are all, fixed. And so with that, thanks for the sponsors. And I'll go ahead and end my time now.
John, thank you very much. You put the scientific in machine learning. That's awesome. Really appreciate this talk and review. Any questions for Dr. Foster? All right. If there are any questions afterwards, please feel free to use chat window. Dr. Foster's contact information, of course, easy to find.